Track 2, Strategic Effect. I'm Sunil Yu. I'm your MC for the rest of this morning. And today, or this morning, the first up is Jenny Wright. Ginger. I'm sorry. Ginger Wright, right? Okay. And she's going to talk about buying blind, how federal acquisition is leaving cyber-informed engineering on the table. I mean, what is wrong with, there's nothing wrong with federal acquisition, right?
Nothing.
Nothing at all. All right. With that, let me turn it over to Ginger.
Thank you. So good morning, everybody, and thank you. Normally, I would talk about cyber-informed engineering and tell you about this approach. But in this talk, I really wanted to look at how could we introduce cyber-informed engineering into procurement, and what are some of the barriers that leave it behind? So I'll start by saying right now, with all of the tools that we've talked about and with all of the ways that we're approaching cybersecurity, if we're approaching cybersecurity, we are not, with traditional digital tools, we're not solving the whole cyber problem. Every major cybersecurity framework was built for information assurance. It was not built to secure a function or a capability. In OT and ICS, our failure modes are physical as well as data-based. And some of the highest consequence impacts that we have to protect against are physical. Function assurance as an approach doesn't appear in any major cybersecurity framework. And I'll show you some examples of that as we go through. And I'd like to look at how we can change that. So I used a word called function assurance, or a phrase, and it's necessary for me to define that. When we think about information security or information assurance, we think about protecting the confidentiality, integrity, and availability of data. That's traditional cybersecurity from the books. With function assurance, we're looking at what a system is designed to do to ensure that it performs its intended physical functions and only those functions, even if it's under adversarial conditions, independently of whether cybersecurity or digital access controls hold. If I just have information assurance, then I am making an assumption that if I control the means for access, all the data pathways into my system, that I'm going to keep the system safe. And we used to call that the hard, crunchy shell with the soft, creamy center. Because if I can penetrate and gain access, then I can gain control. With function assurance, we assume that an adversary that wants badly enough to get past those controls will do that. But once they get in, we want to limit what the system will allow them to do. Based on this, we extrapolated 3 requirements that should be in every operational technology procurement. The first is consequence definition. We used to say a lot, you can't secure what you don't know about. And consequences are one of the natural things that we're trying to secure without most of our cyber teams really understanding them. So in a procurement, whether I tell my vendor about this or not, it's necessary for me, the person who is trying to enact a change through exchanging money with a vendor, to understand what are the requirements, what are my expectations, and what are the unacceptable outcomes that could happen as a result of subversion of whatever I'm buying. The next, and we've heard some great examples this conference, I'm so excited that we're hearing about the application of engineering or engineered controls. What could I put in place that, again, is independent of my cybersecurity that will prevent these undesired outcomes from taking place? In some cases, we've already thought about these things for safety. And so we can take credit for the things that we do for safety and then add things that prevent non-safety related but unacceptable outcomes from happening. And the third is we need to test that this actually works. If I put these engineered limits in place, do they prevent the undesired outcomes that I imagined? And that should be part of every factory acceptance test or system acceptance test to ensure that we understand what we're doing. But today in an operational technology procurement, these things do not exist. So it's easy to look at the vendors and say, why aren't the vendors helping to identify these consequences and engineer them out? And that's a complicated question. First of all, vendors are interested in abiding by standards. There was a time in operational technology, digital development work where a vendor would create a highly couture solution for every asset owner and every deployment environment that they went into. And you might imagine that was a maintenance nightmare. They had to have staff who knew that customers' magical changes in their business model. And vendors have gotten smart and said, you know what? Why don't we come together and we'll define these standards, and that expresses the general sense of what you, the customer, view as the requirements for the products you buy, so that we don't have to meet every single particular interpretation. We just go by the standards. And they design to things like 62443. They design to things like NIST Special Publication 800-82. They design to things like CMMC. There's no incentive for them to go back into the couture world because it's expensive and no one wants to pay for it, and you can't scale it. So the vendors are selling what we are asking for because they expect us to enumerate our asks in standards. So there is a gap. Standards often define what a digital system should be made of, but they don't really address how that digital system is integrated into a physical process. And that is the place where this digital command from a system could make a physical system do something that we have the best opportunity to put in engineered controls or other integrations that would stop this if it could lead to an undesired outcome. So this is an eye chart, and I won't go through every row of it, and I would encourage, take a look at it later. But we wanted to look at some of the standards that we had talked about and knew about and see where they have assertions. Where do they have information about protecting data and particularly controlled unclassified information? Where do they have procurement specifications? Then where do they talk about consequences? Where do they talk about engineered controls? And where do they talk about anything related to OT or ICS? I did this quickly. It deserves a longer analysis, but I'll start. And I'll dive into a couple of these in deeper slides. In general, using this consumer reports model, you can see there isn't a standard that cleanly covers all of this ground. You can also see that some standards are very designed for protection of critical information and less designed for operational technology applications or other environments. Okay. Looking specifically at DFARS and CMMC, that's certainly a standard that military procurements are going to have to leverage. It was not designed to really deal with operational technology, and it was literally designed for information assurance. So the good news is it speaks a lot, and it's a tough contract to live to, about how you stay accountable for the sensitive data that is moving through your system, and it defines it in some very particular ways. But it's very much missing the idea of engineering information being sensitive, and it's really for contractor systems that are processing controlled unclassified information. 62443 is one of the standards that is by design for ICS and OT systems. And it is probably the closest standard to asking for some of the things that I would be looking for function assurance. So on the good side, it defines what risk assessments should be done. It defines a set of security levels, and I have a few quibbles with those, but it does at least lay out what would be different levels of security that a system could or should try to achieve. It sets program requirements for a broad-based security program surrounding ICS and OT systems, and it gives very, very in-depth guidance for how to implement that program and all the different programmatic areas. It has a companion program for vendors so that vendors can align with their part of 62443 and asset owners have their program and find a match in the middle. So that alignment is very useful. Where 62443 currently falls short for functional assurance is that its risk assessment mechanism is based on probability and impact of a compromise of a zone or conduit, an information pathway in the system, rather than the interruption of a critical function. It does ask people to think about critical functions when they design a system, but then the engineering requirements to mitigate any damage or any perturbation of those functions, all of the advice that it gives is digitally based. It also, again, it talks about physical consequences with operational technology systems as one measure for how you set security levels. But once you set that security level, then that consequence that caused you to make the choice isn't tracked as you go through the process. It's dropped, and then you use the security level from that point forward. So ideally, you would set a security level for a reason, but you would keep track of the reason and validate based on it once you did your implementation. Some ask about NERC-CIP. I work a lot with the energy industry, and this is a regulation approach that binds a lot of what they do. NERC-CIP does have things that talk about access control, perimeter protection, configuration management, vulnerability management. It does have an element that talks about physical protection requirement for consequence significant transmission facilities. But it really does not talk about using engineered controls to reduce cyber risk. Even CIP 14 that talks about physical things doesn't require engineering controls that bind cyber physical consequences. So it's not in NERC-CIP either. Given that we don't have standards that drive this into a conversation between an asset owner, an integrator, and a vendor, INL wanted to look at what would happen if we mocked that up. What would happen if we brought a fairly typical vendor with a fairly typical asset owner and had them start talking about these consequence-based issues? What would the discussions look like? Would it be an easy conversation? Where would the vendors go with it? So in that experiment, I've got some results. We simulated the purchase of an advanced distribution management system. This is a very digital system that controls some very physical things. So in that, it was a great example. We were guided by a CIE procurement set of questions that were pulled out of the CIE implementation guide. And on the back, in addition to some stickers, I've got a card that you can take that takes you directly to that guide. We brought the vendor and the asset owner together. We had the asset owner do some homework in advance because they understand the system that the advanced distribution management system was going to be integrated into. And INL stayed as just a facilitator in the conversation to help keep things moving. Our experiment results were that this vendor was focused on compliance with standards. Standards were their love language. It was how they expressed to a customer the viability and effectiveness of their product. And so when we talked about things that were not within the current standards, the vendor really was not able to deal with those effectively. The vendor had concerns about liability. If I, as a vendor, advise you as an asset owner to employ the product in a particular way, now that's tied up in this sale and I may be liable for the outcomes of that advice. So, okay, that was a good result to understand. But they weren't averse to trying to think about this, and they had some suggestions for how we could go forward. They suggested that for common types of systems that energy asset owners buy, that those asset owners work with trade groups or some other entities to think about what would, in a general sense, what would be the worst case unacceptable outcomes that could result from a use of those systems. And if those worst case outcomes were tabulated and provided to vendors, the vendors could incorporate that in how they approach their design. Because those would be shared through the trade organization and not to any individual vendor, it minimized the vendor's sense of liability. And it also allowed them to take a standards-like approach where they weren't designing for each and every customer, but they were trying to move to a general case. So based on their suggestion as a part of this experiment, we did this for the Advanced Distribution Management System. As a result of this, a couple of findings. Vendors can only bound consequences for what they directly produce and control. The vendor producing the Advanced Distribution Management digital system doesn't own any of the physical systems that ultimately that system will control. So if that's where the best consequence or the best mitigations can be placed, that's out of the bounds of any vendor, or at least any software vendor, to touch. So some of this is going to have to be an asset owner or an integrator conversation, because the vendor doesn't reach into the systems that that have the best potential for mitigation. And again, liability. Cyber-informed engineering's benefit was primarily to the asset owner in this conversation. The asset owner got a great deal of in-depth understanding of the engineering endeavor surrounding the acquisition that they were making. They brought in a broad group of stakeholders, and they had ideas for how to design the system beyond just the acquisition that they put in place after the discussion. So that's the good news. I know it's hard to put more responsibility on the asset owner, but in this case, that depth of understanding led to a very different procurement conversation, and it led the asset owner to be very focused in asking how this vendor implemented their standards for particular kinds of digital commands that could lead to unacceptable outcomes. It really focused their attention, and it helped them ask better questions. This experiment also showed that this conversation is just beginning. We are early in how to apply cyber-informed engineering in a regularized, standards-governed procurement process. We have a lot of work to do to get it into standards and to get the whole idea of engineering out cybersecurity risk into standards. And we have lots of time to work with asset owners for how to successfully and at the lowest cost implement this. I do have a bright spot, however. In some cases, the vendor does own both the digital control system and the consequences. And we've had several manufacturers of battery energy storage systems where that is the case. They manufacture a physical system that keeps the chemical part of the battery functioning, that controls how it works, that keeps it cool enough so that it doesn't catch on fire. And they sell that contained system with both digital and physical parts to asset owners. And in that case, we've had several vendors that have been highly motivated to ensure that they can engineer out the potential for digital risk to cause a safety consequence for the asset owners who implement their products. Both vendors have incorporated this. Both vendors were, again, looking specifically at fire risk as the primary consequence that they wanted to eliminate. And they viewed the implementation of engineering controls as a way to future-proof their product in the market, so that 5 years from now, 10 years from now, when we aren't really sure what an adversary is going to look like or the complete complement of tools at their disposal, the vendors that have engineered out those digital consequences at least have a battlefield that's a little more prepared for defense to have a role and a good role. So that tells us that when the consequences are bounded in the vendor's product, they will accept and they will adopt engineered controls. For functions where things are more spread out, we are going to have to look at system integrators and physical infrastructure owners. So, how do we take INL's procurement experiment and bring it to scale? First, we need to convene more of these cross-functional teams. Often a procurement experience, we pass the paper from group to group, stakeholder to stakeholder, but we rarely bring the key set of stakeholders in a room and really explore what are the unacceptable consequences, whose resources will be pulled on to mitigate those consequences, and what we want the asset owners to work through the CIE implementation guide questions before the engagement begins, before they begin to talk to a vendor. We would like to see consequence definition documents that define what are the unacceptable outcomes, where are the vendors' accountabilities within those unacceptable outcomes, where are the asset owners' accountabilities within those unacceptable outcomes, and if there are defined gaps, define them and add them to a requirements list somewhere for the systems engineering effort. And finally, enter that vendor engagement with a consequence-aware posture. Now you know what you're buying, you know how it could go wrong, and what you want to do to mitigate it. As we talked about, this requires a multi-party accountability structure where the asset owner is the one defining the unacceptable consequences. If there is a system integrator, they're involved a lot earlier, not once the cardboard boxes show up and there are bits and pieces to wire together. We have our integrator involved in the consequence definition so that they can help mitigate it. And finally, that digital system vendor has to at least acknowledge the consequences that their asset owner is concerned about that go beyond information assurance, and understand how the controls that are in their digital system perform even a partial mitigation of the probability of that consequence occurring. And our requirement was to make sure that we had actionable advice that you could take home. So my ask, if you are an operational technology or ICS practitioner, run a structured internal consequence exercise before your next major procurement. Actually sit down with the engineering team and the cyber team and the maintenance team and the operations team. Talk about what might happen, what would be the functions that would be interrupted, who would be called upon to deal with them, what are the expectations for the digital portions of the system, and where could the engineering surrounding the system be integrated and improved to limit those consequences. Bring the integrator in. If possible, let them be part of that conversation, and share that approach with peer organizations and sector coordinating bodies. Again, the vendor didn't want to engage at the consequence level, but they very much saw how a set of asset owners that defined these common consequences for the kinds of systems that they buy would improve their engineering approach. If you are a policy or strategy official, one of the things that we need, particularly in NIST Special Publication 882, it is in a revision process. Right now, the families of controls that NIST has integrated are digitally based, all of them. Physics is not in the picture. We need a family of engineered controls. We'd like to pilot consequence-aware evaluation language in existing procurement standards that are used, at least to encourage the conversation, even if the standard doesn't govern how it is answered. Sector coordinating councils could develop common consequence lists by product category. Again, if they all talk together and they define it, there's no sensitivity or intellectual property specifically in those lists, but it could guide vendors to put their focus on the right capabilities. And then lastly, we'd like to engage 62443 to address the consequence verification gap, to put more of the engineering into how they think about operational technology and industrial control systems. Okay, I'll finish with a Josh-esque slide. Every contract that we award without consequence requirements is an unverified engineering assumption. And if you're an engineer, those are harsh words. Every cybersecurity standards compliant system that has unbounded physical consequences is not safe, is not reliable, and is not performant. In other words, it's not resilient to the degree that it needs to be. And we will only stop buying blind whatever our vendors hand us if we start analyzing consequences. Are there any questions?
All right, hang on. Oh, sorry. I would have.
Oh, wait, I'm sorry.
Thanks for the presentation. On the sort of case study you had on the two energy companies, Fluence, and I'm forgetting the other one. What do you think made that successful? Was it they saw an opportunity to pitch and deliver more value to their customers, and so that's why they were building that into the product and then marketing and selling that, or do you think it was something else?
So great question. There were a number of factors that made this successful. First of all, several high-profile battery energy storage fires. Certainly no evidence that those were cyber-caused, but it's enough awareness that that is a very deep concern of asset owners. The second thing that made it successful is concern over the supply chain for battery energy storage systems broadly, and the desire for vendors to show that they're mitigating those supply chain concerns and those digital risks however they can. And this idea of this is a product that's got to live in the market for 20 years. For the vendor, the thing that made the engagement successful was that they brought a very broad team. They brought their cyber team. They also brought their engineers and their product managers. So in that room, thinking about mitigations, we had the right groups who could say, well, wait, how does that message queue system work? And what is the actual message that passes? And what happens if the fan doesn't get the message at the right time? How does the device know what temperature it is? With being able to trace those questions back and forth from the digital instantiation of the battery to its physical instantiation was really, really helpful.
Being able to influence change in NIST standards, it seems pretty straightforward, right? There's a call, you provide input, there's a timeline for review. How is Idaho or other national lab stakeholders informing change today for in the context of IEC 62443?
Great question as well. We are involved in several of the working groups with IEC 62443. We're one voice, so we can't overtake the conversation with all of the other thousands of people that are there, but we are putting a plug in for engineered controls. With every standard, they go through cycles, and you've got to catch them at the time that the revision is open. You've got to catch the conversation at the right place, but there are a lot of stakeholders who are trying to get that started. Things like this talk, things like having a chance to talk about cyber-informed engineering with groups like this widens the number of interested participants and raises the chance that a standard will pick it up.
Okay, I had two questions. One is, how is this different than threat modeling as a requirement?
So with a threat model, typically you think from the outside in. What is this threat actor interested in? How are they going to find out about my system? You work the kill chain inward. And that's often how we do our threat modeling. With consequence modeling, I'm working from the system functions outward. So absent any threat, I don't care, no Tom Clancy novel here. What is the system supposed to do? I don't yet think about who would be motivated to stop it. It's what must it do? What can it never do? And how can I make that stop? The benefit of that approach is once I have these engineered controls in place, not only do they help me defend against attackers, which is good, they also help me defend against undesired automation or autonomy. If a system tries to do a thing that would also be bad or tell a human to go do the thing, it stops that. And it protects me from amateurs or, sorry, idiots, people who just make a mistake and do the wrong thing. If the system can prevent that, again, now I'm protected there. So that's a much greater scope of resilience outcomes than just threat modeling.
Okay, and then the second question, following up from that is functional assurance. You're trying to bound what the what the product or capability is supposed to do, but effectively, that almost sounds like what the same right to repair. Well, some of the things that we're seeing with right to repair considerations. You're locking down functionality that I actually want to tap into. You're preventing me from actually using that function, even though it's capable of doing something. You're limiting my ability to actually unleash that. Is that a vendor restriction or is that a customer restriction? Like, how do you see that sort of battle playing out?
So typically, cyber-informed engineering right now is done by the asset owner. So they are locking out functions that they deem unsafe or untoward for implementation in their environment, whatever that means. That old quote, turn it up to 11. No, 10's as high as it goes. And there's a stop that says you can't turn that dial any further. So that kind of thing is what the asset owner is doing. In the case of these vendors, what they found were potential safety-related functions that if digital technology was used in a way that was unintended, it could cause a safety function. So these are functions that it's very unlikely that their asset owner user would have wanted at all.
Okay, great. Thanks very much.